Good morning, ladies and gentlemen. I'm going to be starting chapter 19, Magnetism, with a demonstration. Right in front of you, what we have is a generator, and I have another hand crank generator, so I'm going to be giving you guys a demonstration. So, just to show you guys how big it is, you can see my hands on it. Okay, good. You can see my hands on it, and I'm going to kind of flip it so you can see on this back side, we have a crank, and I can turn this crank, and when I turn this crank, it's going to turn around these coils, which are inside a magnet. So guess what? Everything with magnetism has to do with magnets. Probably figured that out. Okay, so what I'm going to do is I want you to draw your attention. Right here we have an LED, a diode LED, and I'm going to come over here, the back side, and I'm going to turn the crank. What did I do? I turned the crank, which made the coils turn around inside the magnet, which produced electricity, and so current could flow and turn the LED on. So there's your first example of hand crank magnetism. Okay, here I have another example of a generator, and it's a hand crank generator. So you see the handle here that I can turn around, and you can see on the end here I have a little itty bitty light bulb. Can you guys see that? Little itty bitty light bulb. And now I'm going to see if I can turn it. And what do you know? The light bulb turned on. So what I'm doing is I'm generating electricity because there's magnets. You can't really see the magnets inside this little silver compartment. There's magnets, and because of the magnets, there's a magnetic field. And because I'm going to be moving something inside those magnets, I generate a current. Okay, that's my second example. All right. Now, what I have here on the table are a whole bunch of magnets. This was not easy for me to do because, as hopefully some of you have experience with magnets, the magnets either want to come together or come way apart. First thing I want you guys to know about magnets, let's see, is that going to be difficult? That there's a north and there's a south. A north and a south. See if I can push this one up without it wanting to jump and attached to one of the other ones. There's a north and a south. Every magnet has a north and a south end. I have these teeny tiny magnets. Here we go. Teeny tiny magnets, a whole bunch of teeny tiny magnets that are, they're hard to take apart. Let's see, hard to take apart. All right, I was able to take them apart before, but they're really tough to take apart because the north and the south are all smashed together, which is how they want to be, all smashed together. What I want you guys to see, though, this row right here, you'll see these little lines. This was before my time, but these used to be one bar, and they broke. So I now have here 3 pieces. And they all want to stick together. What's interesting is when you take a magnet and break it apart, you will have a south and a north. Every time you break a magnet, there will be south and a north. Look at that. Everybody wants to play now. All right, everybody wants to join together. And the north and the souths always come together. So if you guys can see that there's an S there and there's a north part right here. The south and the north attract, opposites attract. The south and the north attract. If I try to break these apart, try to break these apart. There we go. So this used to be part of one of so I know this says south, this must be north, and that when these got broken, this was south and this was north. If I took this, and it's kind of thick, and if I could somehow break it apart, I'd end up with another south pole and a north pole. So same with these magnets. I have a bunch of south and a north pole. Can I take these apart? Here we go. These little ones I was trying to take apart, it's really hard to take apart. There we go. You can see. Now I have a really, really big magnet. What do I mean by big? An even stronger magnetic field. And you can see all these things that jumped up on top. I was trying to take it apart before, and I was not having a lot of success. I could push them apart. So the magnetic force is so strong and it's attracting the metal for ferromagnetic, F-E-R-R-O, ferromagnetic, because it will either attract or repel to north or south. All right, I have a whole bunch of magnets. These are the magnets that you guys would have gotten to play with in the classroom and be able to experience the attraction or repelling. So you can tell that north and south attract, but ooh, you can actually feeling it pushing away. You guys can see it moving away. Ah, it does not want to be near the South Pole. All right, I want you guys to learn now, how do magnets affect compasses? All right, let's stop the moment here. Okay, I have here 8 different compasses. So some of these, hopefully you guys have been able to play with sometime in your life, a compass. These are probably ones you've seen. These are a little bit bigger. And the bottom line about the compass is you can rotate the bottom however much you want, but the needle is only going to move according to the Earth's magnetic field. So as you probably know, the compass is used to tell us where north is. So the needle is pointing to north. Well, you got to pay attention to which one it is. You can see that 1, 2, 3, 4, 5, all of them are mostly going to the left here. So I'm here in Fair Oaks, and north is kind of pointing in that direction. And you can see that in this case here, turn the base of it, you can see that even if I turn it around, once it stabilizes, they pretty much are going to point in the right direction. Now, you'll notice that in some of these cases, I have it white pointing over here, but red pointing that direction. And I'll explain that in a little bit. What I want you guys to know is the Earth, our Earth that we're standing on, we're sitting on right now, has a north and a south pole. But the Earth's magnetic field, a little different. So even though we call north the North Pole way up at the top, and I'll show you guys a handout where I have this, it's really the south magnetic field. Why? Because the north part is going to be attracted to the south pole, the south magnetic field. Again, we know that north and south attract each other, so the needles are going to, I'm going to show you why that moved. The needles are going to move depending on where north magnetic field is. Well, in my hand here, I have a magnet. And watch what happens when I take this magnet and I'm just going to put it over, look at that. So these little needles are very sensitive to the magnetic field. So right now, the magnetic field produced by this magnet is a lot stronger than the magnetic field of the Earth. And that's why I can force these guys to go nuts, okay? These little arrows to go around, all right? So I take my magnet away, and I had a really big one, take my magnet away and have these needles kind of calm down and stabilize. So you'll notice that some of them are exactly flipped. This one here is exactly 180 degrees off, and this one's exactly 180 degrees. Last year, I let the students play with all the magnets as much as they wanted and these compasses, and these aren't very expensive compasses, so it is possible to demagnetize and then remagnetize thin, cheaper pieces of metal. And that's probably what happened here. It's still pointing in the right direction. It's just that this one should be red and this one should be white. And it's still pointing in the right direction. So it's still being sensitive to the Earth's magnetic field. All right, I'm going to show you guys a handout. Pause. All right, so I'd like you guys to take a look at this handout. See if I can make it a little bigger, maybe. And what we see here is I've titled it Chapter 19, Magnetism. So here's what you want to know. When you're looking at a magnet, one side is called the north side and one side is called the south side. So what's the direction of the field? It goes from the north to the south, always from the north to the south. So magnetism, result of electrical current interacting with magnetic materials. Two charged particles produce a circuit, and all magnetic fields are the result of an electric current. So anytime you have current, you're going to have a magnetic field. Oh, the other thing I want to make sure you understand, when I said it didn't matter how many times I break my little magnet, I will end up with a north and south end. So there's no such thing as a monopole, always dipole. Okay, you're always going to have north and south. All right. So the electrons in orbit form the north pole, and the other side, it's the south pole. So we actually call these the north pole and the south pole of each and every magnet. So here's what I was talking about. If you look on here on the left side, we have our Earth. Now the Earth isn't quite standing straight up, so we actually have it at an angle. So notice how the north geographic pole, in other words, way up north above Alaska, is actually the south magnetic pole. And that's why the north part of the compass needle will point up to the north, because it's really pointing to the south magnetic pole. And that's why you can say that the south geographic pole is called the what? North magnetic pole. Okay, see if I can make this a little smaller. There we go. All right, we'll be talking about these formulas later, but here's my example. We start with one big magnet, cut it in half, we'll end up with another north and south pole, Take these pieces and cut them in half, and we'll have a north and a south pole, and a north and a south pole. So, most significant difference between a magnetic field and magnetic flux. What's a magnetic flux? The magnetic field is the region around the magnet where the moving charge experiences a force. Actually experience. I actually could feel pieces pushing apart from each other. That's the magnetic force. Okay? But the magnetic flux is the quantity or strength. So that's where we get numbers. How strong is it? The magnetic flux or the strength of the magnetic lines? Okay? Pause here so I can switch. All right, I lost my pause part. Okay, pause recording. Okay, now I'd like to show this short little video about the magnets and its magnetic forces.
The parts of a magnet where the magnetic effects are strongest are called poles. Magnets have a pair of poles, a north pole and a south pole. A magnet's north pole always points north, and its south pole always points south. Poles that are alike repel each other. For example, two north poles repel one another. Likewise, two south poles repel one another. However, two unlike poles, north and south, attract one another.
Okay, all right, I want to show a slide here, slide number 12. Slide number 12. Hopefully you guys can still see this. There we go. All right, so hopefully you guys can see this. This is a good representation of our planet Earth. And even though we go straight up and down vertical and call this part the geographic North Pole, we know that our magnetic field is actually askew, and a diagonal. So up here, close to the geographic North Pole, is the magnetic South Pole. And our geographic South Pole is close to the magnetic North Pole. All right, now I want to show you guys a video about magnetic filing, about the compass needle. Get that one.
The north pole of a compass needle points in the direction of a magnetic field. To show directions of magnetic fields in drawings and photographs, we use a set of three symbols. A series of arrows shows the direction of a magnetic field in the plane of the paper. A series of dots for the heads of the arrows represent a magnetic field pointing up from the page. A series of X's for the tails of the arrows represent a magnetic field pointing down through the page.
This is important because we need to be able to talk about where the magnetic field is versus where the current is flowing. And that's going to require us to talk in 3 dimensions. So again, we're going to be using circles and we're going to be using X's. So on the plane of this piece of paper, we see some arrows here. And what you're going to be having to keep straight is where the current is versus where the magnetic flux is, magnetic field is. I'll play this one more time.
The north pole of a compass needle points in the direction of a magnetic field. To show directions of magnetic fields in drawings and photographs, we use a set of 3 symbols. A series of arrows shows the direction of a magnetic field in the plane of the paper. A series of dots for the heads of the arrows represent a magnetic field pointing up from the page. A series of X's for the tails of the arrows represent a magnetic field pointing down through the page.
Okay, and the last thing I want to show is a little short video. Hopefully it's still up. Here it is. Okay, what we have here is a wire and a current going through the wire. And you have to understand what electrical filings are, metallic filings. Say you took some sandpaper and if you could get little pieces of metal off, tiny, tiny little pieces, as if you're sawing off sandpaper off of wood, but instead of metal, called metal shavings. And let's see if I can make this bigger. And here we go. Start from the beginning. What they're going to do is run a current through the wire and see what happens to all the little metal shavings that happen to be nearby. Here we go.
A wire that has current flowing through it produces a magnetic field. Here we see iron filings forming a pattern due to the magnetic field created by the electric current. The direction of the magnetic field is determined by the direction of the current in the wire, according to the right-hand rule. If the thumb of your right hand points in the direction that positive current is flowing, then the magnetic field goes around the wire as shown by the curling of your fingers. In this example, the current is flowing upwards, so the magnetic field points in a counterclockwise direction. The symbol B refers to magnetic field, and the symbol I refers to electrical current. A wire that has...
All right, let me see if I can go back to that picture there. The right-hand rule. That's not going to help, huh? Okay, see right here.
I refers to electrical current. A wire that has...
All right, well, that's not going to help. Bottom line is, it depends on the direction of the current. Is the current going up in that wire, or is it going down? Then we would know the direction of the magnetic field. So I'll talk more about that next time. And that has to do with the right-hand rule. Okay.